Hey, what's up, special people? Gather around here, you student engineers, uh, engineering practitioners, and maybe a layman out there who feels he wants to learn something on design and construction of structures. So today we're going to learn to design an element here, strip footing. Of course, strip footing is a shallow foundation. Is a shallow foundation that provides basically a linear support, or maybe a continuous and linear support to the load-bearing walls. They are mostly used on load-bearing walls or closely spaced rows of columns for that case. But at this point, we're going to design it to be used on a load-bearing wall, like so. So let's delve straight into what we have today. Remember, this design was originally done by Bromtech, and I'd just like to make a recap on one or two so that we learn, especially for the student engineers out there who are aspiring to be structural engineers. So the design in itself, of course, begins with you'll have your design information like so, with your number one here being the yield strength of steel at this point as 500 newtons per millimeter squared. Your concrete compression strength, density of concrete, of course, is usually 24 kilonewtons per meter cube or 25 for a reinforced one. You'll have the density of masonry. At that point, Bromtech tested the density of the masonry he was using and found it to be 20 kilonewtons per meter cube. Concrete cover. Concrete cover with reference to BS 8110 uh, provides values for depending on the exposure conditions. So at this point, we'll be using 50 millimeters. The wall thickness, of course, 200. Wall height for foundation was 1500 millimeters plus the 300 millimeter uh, height for the load bearing wall, giving a total of 4500 millimeters. Then we come to the presumed allowable soil bearing pressure. This one is extracted from the BS 8004 table 1, which comes handy. The BS 8004 comes very handy and provides a lot of information. So it was taken to be 200 kilonewtons per meter squared. Should be per meter squared. Thank you. Then we move straight to the first step, which is the loading. You perform your loading as and then you perform your load combinations using again making a reference on BS 8110. You can perform load combinations here. The SLS using 1.0 GK and 1.0 QK, and your ultimate loads with 1.4 GK and 1.6 for QK, like so. Then next, you move to foundation sizing, perform your foundation sizing, uh, which is more or less similar to that of, at this point we did minimum foundation width B using the formula service load over net allowable bearing pressure. So remember in pad footing, you'd use uh, this formula here would give you the minimum area, of course, the minimum, the plan area, that is the plan area. So at this point, we would use 0.108 meters. Then if that is per meter, remember we are calculating using per meter run. This design was done per meter run. Then you move next you move to determination of the soil bearing pressures that way. Then you move to calculation of your effective depth. Effective depth is for the footing is similar to that of slab, is determined in the same way as the effective depth for footing, which is the distance from the top part of that element to half the bottom of the reinforcement. Then straight would move to cantilever moment calculations, which is done at this point to verify the concrete capacity and of course to determine the steel reinforcement. Then straight you move to shear checks, then longitudinal bedding design. Remember this design here, the design for cantilever moment comes about because of because uh, the load bearing walls sits at the middle of the footing, therefore creating a point load to the footing, and the footing itself also experiences a pressure from the soil from through the entire width. Therefore, these two parts act as a cantilever because of because they are hanging. They are somehow hanging because of the pressure from the soil that way. So we design for them. Then the longitudinal reinforcement is this one here, the three, which are done to handle uneven soil settlement, and it assumes that the footing is simply supported. It assumes that the beam is a simply supported beam. Rather, the footing is a simply supported beam spanning over a gap in the soil. That is why we borrow calculations from our knowledge in theory of structures there, and then you design for the reinforcement like so. Then after that, you would then detail your footing like so. So this one is a sketch of the strip footing. So just a reminder to the students out there, do your thing, do more designs, uh, get to know, get to understand, or maybe to read, to use your BS codes and maybe Euro codes depending on the country from which you are. And I think that's it for today. See you next time.